All right, today we're doing 2.5 algebraic reasoning. So we've talked about inductive reasoning, deductive reasoning, and now we're doing algebraic reasoning. Okay, so we're going to be looking at the algebra behind the math. Our objectives today are to identify key subsets of the real numbers, so the natural, the whole, the integer, the rational, and the irrational numbers, which we talked about a lot in Algebra 1. Identify and apply properties of real numbers and equality. And we're going to write some algebraic proofs today. All right, so first up, our sets of numbers. Okay, you'll notice that we have this, this is a Venn diagram. I know it doesn't look like one, like you typically say, but it is a real Venn diagram of our real numbers down here. Okay, so the real numbers are divided into two main parts. We have rational, which is Q, and irrational, which are Q prime. Okay, so our irrational. Inside of our rational, we have the integers, which are Z, the whole numbers, which are N, or W, pardon me, and then the smallest subset is our natural numbers. Okay, notice that our natural numbers, right, are 1, 2, 3, 4, 5, our counting numbers. They are a subset of the whole numbers. So we might say natural numbers are a subset of whole numbers. Okay, because they're inside of there. And we could also say that whole numbers are a subset of integers. So the whole numbers are a subset of integers. Because integers are inside of our rational numbers, we can say integers are a subset of our rational numbers. And since rational is inside all of the real numbers, we can say our rational numbers are a subset of our real numbers. But so are the irrational. So we could say irrational numbers are a subset of the real numbers. Okay, so those are lots of different subsets that we're talking about. Okay, they're all subsets of real numbers. So you could say the natural numbers are a subset of the real numbers. Yes, absolutely. Okay, you could say whole numbers are a subset of the real numbers. Yep. Okay, all of this is review from Algebra 1. Woohoo! Right, all that vocabulary. None of it's new. Okay, so, and that's just what this chart is down here as well. We've just got some numbers in there for your examples. Okay, so you have some natural numbers, some whole numbers. Notice it's just 0. The only number that's whole and not natural is 0. Our integers, that's when we're getting into the negative numbers. The rational numbers is we're getting into those fractions, okay, or decimals, but they have to terminate or repeat. So these will terminate or repeat. Then we have some irrational over here that will never terminate or repeat. Oh, it's missing that repeat on there, so you might need to write that in there. Okay, so they'll never terminate or repeat for irrational. Okay, then we've got some properties of real numbers and equality that will be used in your reasoning. Okay, so we have some real number properties because they're all real numbers, but we have the identity property, right? That's when we have any number and we add it to 0, we still get that real number. Or if we use it in the multiplication, any number times 1 equals that number. So these are the properties that we can possibly use in our proofs. Okay, we're going to be doing proofs on the back of this, on these notes. So these are some of the reasons that we can give. Okay, the inverse is when we add a number to the negative of it, right? A number plus its negative is the inverse. So it's 0. Or a number times its reciprocal equals 1. All right, that's the inverse property of addition, the inverse property of multiplication. We have the commutative property. Okay, so if we have a plus b, but we want to change that to be b plus a, we've applied the commutative property of addition. If we have a times b and we want to change it to b times a, we move the order around, we've applied the commutative property. The associative is where we just change our groupings, right? A and b were grouped together, we changed it to group b and c together. The distributive property is when we have a times the quantity b plus c, and we change it to be ab plus ac. Okay, so you know all these properties, but we're going to have to use them and state them as some of our reasons. Now, the properties of equality. Okay, so these are the things that can go in your proof again. The reflexive property is saying that A equals A. Okay, that's awesome. The symmetric property says if A equals B, then B equals A. So they're symmetric, there's symmetry there. The transitive property, we talked about with deductive reasoning, transitivity, okay, is if A equals B and B equals C, then A equals C as well. The addition property of equality, if A equals B, then A plus C has to also equal B plus C because A and B were equal. So that's the addition property of equality. Where the multiplication property of equality says if A equals B, then A times C has to equal B times C because A and B were equal. So there's some good properties there for us to use. Then we have an equivalence relation. Okay, an equivalence relation is a relationship that is reflexive, symmetric, and transitive. So it has the first three properties of equality. So the equality of real numbers is an equivalence relation. So the equality of real numbers is an equivalence relation. So the relationship is reflexive, symmetric, and transitive. All right, the substitution property we have next. If A equals B, then A can replace B in any mathematical statement. So that's substitution. Okay, if A equals B, A can replace B anytime. That's awesome. Now, the trichotomy property then says for any two real numbers, A and B, exactly one of the following is true. Okay, so this is trichotomy. Exactly one is true. Either A has to equal B, okay? A has to be less than B, or A has to be greater than B. One of those three things has to be true with every single pair of numbers, okay? All right, let's look at example 1 then. So I'm obviously going to have to move my paper up, but make sure you're looking at these things. So example 1 says, name the property that justifies each statement. So if 5s equals 60, then s equals 12. If 5s equals 60, then s equals 12. Sorry, if 5s equals 60, then s equals 12. What property do you think that is? All right, so we're dealing with multiplication, right? 5 times s. So this is the multiplication, and I'm just going to put mult, period, property, so prop, of equality. Because they would have had 5 times 12 equals 60, right? And then 60 equals 60. So they're doing multiplication right here. The multiplication property of equality. Those two things are equal. How about the next one? If 2x plus 3 equals y, and y equals 5x minus 7, then 2x plus 3 equals 5x plus 7. So notice that both of these equaled y. And then we took what this y equaled and replaced it here, right? That's what they're saying if 2x plus 3, or then, pardon me, 2x plus 3 equals 5x plus 7. So what property would you call that one? Okay, so this one could actually have two. I hope maybe you saw them. So this could be the transitive property of equality. Or this could also be substitution. Okay, because you're substituting one into the other. So either of those. So sometimes they have similar things. You could use either one. All right, how about C? If p minus 7 equals 10, then p equals 17. Okay, well, we're doing subtraction here, but if you notice up there, there was no subtraction. There was no subtraction equality, was there? No, there wasn't, but this is the same, like subtraction and addition are equal. So this would be the addition property of equality. Because addition and subtraction are inverses of each other. Okay. All right, and how about D, this last one? If 4t minus 1 equals u, and t equals 8u, then 4 times the quantity 8u minus 1 equals u. What on earth just happened? So sometimes you have to break it down, right? We've got 4t minus 1 equals u, and t equals 8u. So we've got this t equals 8u. Then, now all of a sudden we have 4 times 8u instead of 4 times t. So they took this 8u and they put it in for t, and then they kept the rest. Minus 1 equals u equals u. What property do you think that is? Good. That one is very clearly substitution. It is not transitivity. That is the substitution property. All right, good. So now a proof. Let's look at this. A proof is a system of reasoning or argument to convince a person of the truth of a statement. We are trying to convince someone. Okay, this is where it's great to come back, like, I know that a lot of times we think that math doesn't really matter so much to like your life, but like in math you are learning, especially in geometry, you are learning to argue and to convince a person of the truth of something, which is going to serve you well beyond just math in your real life. Okay, are you going to use are you going to have to write proofs when you get older? Odds are no, you're not. Not unless you're really nerdy and you love geometry and you go on to teach it or something ridiculous like that. But you are going to have to be able to convince people of the truth of the matter, or at times. So that is where geometry is going to come into play in your future. Okay, algebraic proofs then consist of a series of connected algebraic statements with their supporting reasons. All right, so we're going to get into a few of those on the back, just some algebraic proofs. All right, so first up, we want to complete the algebraic proof. Notice we're going to use, this is called a two-column proof. Okay, so it indeed has two columns, right? Instead of writing whole sentences and paragraphs and things like that, we're just going to do a two-column proof. Notice the left side is always the statement of what's happening. The right side is always going to be the reason. Sorry, I had to erase this one a little bit here because the printer wouldn't work, so I had to erase some stuff that I already had written, and it just shows up here. All right, so to do this proof, we're going to look at what we are given here, the information. So the first one is, the first thing that we have is always given. This is the information that's given, and 5 is, they usually tell us that that's the conclusion. That's where we're supposed to get to. And we have to map out what happened in between. So in this first problem, we have 3 times the quantity x plus 1 minus 2 times the quantity x minus 4. And that equals 4x minus 11 minus 5 times the quantity x minus 6. So how do we get from statement 1 to statement 2? What do? Well, now suddenly we have 3x plus 3. We had 3 times the quantity x plus 1, and now we have 3x plus 3. So what did we do from here to here? Right? That's the distributive property. How about here? 2 times the quantity x minus 4. That became 2x plus 8 because we had our negative 2. 4x minus 11 minus 8. Now we have negative 5x. Negative 5 times negative 6 is a positive 30. So this, step 1 to step 2, we applied the distributive property. That is it. The distributive property. Okay, now we need to look at what did we do to get from step 2 to step 3. So what happened here? We had 3x plus 3 minus 2x plus 8, because I'm just looking to my equal sign, and now I have x plus 11. Well, wait, if we did 3x minus 2x, that got us x. Positive 3 plus 8, that gets us 11. 4x minus 5x, that would give me negative x. Negative 11 plus 30 would give me a positive 19. Like, we just simplified or combined like terms. That's all that happened right here was we simplified. Or you could say we combine like terms. So we haven't even used any of the things on the top or on the front sheet, right? Not yet. We'll get there. All right, next up. How do we get from step 3 to step 4? How do we get from step 3, so x plus 11 equals negative x plus 19, to step 4, 2x plus 8? Well, if I was looking at this, I would say that I added x to both sides, and I subtracted 11 to get here. So if I'm just doing addition and subtraction, that's the addition property of equality. So the addition property of equality, and it's of equality because we're doing it to both sides of our equation. We didn't just do one side. Okay. All right, next up, how do we get from step 4 to step 5? So how do we get from 2x equals 8 to x equals 4? Oh, well, we just divided by 2, right? Now we have x equals 4. But there's not a property for division. So what is it? Multiplication, okay? It's the multiplication property because they're inverses. So the multiplication property of equality. Because again, you could think about that as saying, well, like 2 times 4 is equal to 8. So we've got that multiplication in there. All right, so let's take one example of an algebraic proof. We're just going from step 1 to step 2. Why? What happened? Okay, example 2 is going to look a little bit different. Still a 2-column proof, but this time we're given some reasons and we have to do some of the statements. Okay, and sometimes we have to do both. So in this first one, negative 3 times the quantity x plus 6 equals 6x. Okay, that's given. What should we do? When we see this problem, what should we do? Well, we should distribute, right? So we're going to write over here that we're going to use the distributive property. We're going to apply the distributive property. And that means we're going to have negative 3x. Negative 3 times a positive 6 is going to give me negative 18. And that's going to equal 6x. Ta-da! All right. So on the next one, what would you do next? And it says you're going to use the addition property of equality. Okay, so if you're going to do that addition property, maybe you should add 3x to both sides, right? You don't have to show that in your proof per se, but that means we're going to be left with, after we do this, we would have negative 18 equals 6x plus 3x equals 9x. Oh, time out. They have simplification separate. So this is one thing that sometimes creates a hiccup when we're trying to follow these. So kind of make some of these mistakes on purpose. So in this case, when it's broken down into addition property of equality and simplification, what that would look like is we're just going to have the negative 3x minus 18, and then we could say, but we're going to add 3x to that side. And that's going to equal the original 6x, but we're going to add 3x to this side. So instead of balancing it, and you will see that often in this book and other resources, they actually write it on both sides and show you that it's the addition property of equality. And then the next step is the simplification. So the next step would be, oh, this is negative 18. Pardon me, let me change my color back. This is negative 18 because these canceled. And 6x plus 3x is 9x. Okay, so they're taking that. I would personally show that in one step, but the textbook and some resources will show it in 2 steps. Okay, so we're going to kind of keep that pattern going. All right, so then what would you do next here? Okay, maybe you're thinking divide by 9. You could also multiply by 1/9, however you want to do that. But again, we're going to step this out into 2 steps, okay, because they did addition property and then simplification. So we're going to do -18, and I'm going to write it as times 1/9, okay, instead of dividing by 9. And that equals 9x times 1/9. Okay, so what property did we just apply here? Great, the multiplication property of equality. And again, I show you the multiplication because it's the same thing as dividing by 9. It's okay. We can multiply by the reciprocal, which again helps us understand it's the multiplication property, all right, or the inverse property. You could use that one as well. Okay, then it said the next step is going to be the simplification. All right, so if we do the simplification, -18 times 1/9 is -2. 9x times 1/9 is 9. Okay, so you can have -2 equals x. However, and I didn't show you this, it says prove if -3 times the quantity x plus 6 equals 6x. Okay, so that's what we put here because that's what we're given. Okay, then this is our premise. We have to prove that x equals 2. Well, at step 6, we haven't exactly proved that. We proved that -2 equals x, and I know it's the same thing, but it's a proof. You have to prove every single bit. So this is not acceptable. We have to say, okay, this is the same as x equals -2 because of what property? What property says that this is the same as this? Spell it out for me. Symmetric property. Okay, this is the symmetric property of equality. Okay, you have to spell out every single thing. I mean, and I don't mean spell it out like obviously I'm using prop for property. What I'm saying is you have to explain why for every single one. Okay, you have to give the reasoning. That is what geometry is all about. All right, example 3. Now, let me do a better job of this one. In example 3, we are given the figure with x dash y dash z. So x, yeah, we can just read it like that. And we know that xz is equal to 35. We need to solve for b and justify each step. Yikes. Okay, so we've got a lot. So what is our first statement here? What are we going to put there? And it could be more than one, because here we're given 2 different pieces of information. We're given x dash y dash z. Remember that this means that y is between x and z. And we're given that xz equals 35. The measure there is 35. So that's what we put here. In our statement, we're going to put x dash y dash z, and we know xz equals 35. Okay. This information was given to us, right? It says given. So for the reason we say, hey, it was given to us. That's why I wrote it. That's it. Okay, then step 2 says, hey, you need to use the definition of between. Well, we might have to look up the definition of between and recall that. But the definition of between goes back to this betweenness. Okay, the definition of between says that in this case, xy plus yz has to equal xz. Okay, so that's saying the distance between x and y, this segment, and the distance between y and z, this segment, has to equal the distance between x and z. So this entire segment. That's just the definition of between. That's all. Okay, so I'm going to erase this because we might need some more workspace. Okay, then now all of a sudden we have the quantity 4b plus 3 plus 7b minus 1 equals 35. Well, where do we get that from? Oh, it's because we said xy. Up here we said xy. xy is equivalent to 4b plus 3. Plus, there's our plus sign, yz. yz is equivalent to 7b minus 1. And we know that xz is 35 because that was right here. So see how we're putting these two pieces, step 1 and step 2, we're combining them in step 3. So what reason are you going to give for that? What did we just do? We took information we had here, right? These 3 parts, and we took information we had here, and we took information we had here, and we substituted them into here, to all this parts. So what did we do? We did substitution. This was substitution. We took what we knew, we substituted it all together. All right, what can we do after this? Yeah, like if you were doing this algebraically, right, wouldn't you do 4b plus 7b to get 11b? And 3 plus negative 1 to get a positive 2 equals 35? So what did we do there? All right, you can call it simplification. You could call it combine like terms. Either one of those is fine. Because that's what you did. All right. Then what? What could we do next? Oh, we could subtract the 2. Okay, so we're not going to subtract this, like do this all out. We're just going to subtract the 2 to balance, right? And write our next one. Have 11b equals 33. That would be my preference, okay, to save you some steps. What property did we just apply by subtracting 2? Great, the addition property of equality. So the addition property of equality. All right, then what would we do to solve? Well, we would divide, right? We divide by 11. Again, you don't have to show these steps in a proof because you're doing all the reasons. I'm just showing it to you so you can see we balanced it. So then we get b equals 3. And what property did we just apply there when we divided by 11? I know it seems backwards, but the multiplication, good. The multiplication property of equality. I hope y'all can read cursive. Again, if not, at least write it down as I'm saying it. Or you can back it up and hear me say it again. So the multiplication property of equality. So there are 3 algebraic proofs. Your first proofs you're going to do in my class this year are right there. So that's what we're going to be working on the rest of the year is some proofs. Okay, not always algebraic. They're going to get harder than that. But we're going to start off with algebraic ones because you're more comfortable with algebra than you are with shapes yet. All right, have a great one, and I'll see you later.